start presenting your report. Okay.
Um, Good morning po. Ang di-discuss po namin ngayon ay about sa time history development. And this introduces po the idea of how we can generate and prepare actual earthquake histories to use in a response analysis. So basically po, mag-a-analyze po, um, i-analyze po natin yung time history ng actual earthquakes and dun po tayo magbe-base sa pagde-design po kung paano po yung magiging response ah, design spectrum po ng ating gagawin na structure. Ayun po. Then, time history analysis. Time history analysis is a step-by-step analysis of a dynamic response of a structure to a specified loading that may vary with time. Time history analysis is used to determine the seismic response of a structure under dynamic loading of the representative earthquake. Time history analysis is the use of an earthquake time history to evaluate the response of your system. Can be performed for both structures and soil. So yun po, katulad po ng sinabi dito, um, ginagamit po ito to analyze po both structures and soil. Edi parang mostly used po ito sa structural engineers and geotechnical engineers. Marami pong gumagamit nito na ganitong klaseng engineer sa field po. And ito po yung ito po. Ito po yung frame po ng isang structure na ito po yung example ng isang frame ng isang structure. Ito po makikita po ninyo dito sa ilalim. Ito po may mga springs, ayan po. And diyan po generate yung ground motions. And 'di ba po pag earthquake, yung ground motions po at sa soil po nagsa-start. Tapos dun po, ito po yung mga nakabaon po sa lupa and then diyan po magsa-start yung ground motions pataas po sa ating structures. And then magse-shake na po yung buong structure natin. And yun po yung mismong goal po ng time history analysis. Ang goal po ay how do we pick up the time histories that are going to get us to really close to our target codified spectral acceleration to our period of interest. I think yun po yung parang pinaka-basically na goal po natin na magamit po yung time history ng real history po ng earthquake para po sa pag-analyze po ng ating structure. Ayun po. And there are two main methods po to get our time histories para po makakuha natin yung desired design spectrum. And we have time history analysis and spectrum matching. Time history analysis. In time history analysis, the structural response is computed at a number of subsequent time instants. In other words, time histories of the structural response to a given input are obtained as a result. A full-time history will give the response of structure over time during and after the application of a load. To find the full-time history of structure's response, you must solve the structure's equation of motion. And time history analysis is divided into two, the linear and the nonlinear. Linear time history analysis calculates the solution to the dynamic equilibrium equation for the structural behavior, displacement of displacement, member force, and etc. at an arbitrary time using the dynamic properties of the structure and applied loading when a dynamic load is applied. While the nonlinear is is the known for simulating a structure behavior under severe earthquake or more than other methods. And then this is the ano naman po, definition of spectrum matching. Response spectrum analysis is a linear dynamics statistical analysis method that measures the contribution from other natural mode of vibration to indicate the likely maximum seismic response of an essentially elastic structure. Response spectrum analysis provides insight into dynamic behavior of measuring pseudospectral acceleration, velocity, or displacement as a function of the structural period for given time, history, and level of damping. I-discuss po namin parehas ng time history analysis and spectrum matching, pero po sa sunod na grupo, mas i-elaborate po nila yung spectrum matching po. And next po ay, yan, time history scaling po. Si Ate Angelica po ang magdi-discuss po nito.
Good morning po. Time history scaling. Time history scaling is involved modifying a time history scaling and our time step to try closely match and design response spectrum. In addition, we try to make the smooth average spectrum fall within a specified tolerance of the target spectrum because impossible to get this tolerance over the entire spectrum. We typically focus on the period range of the interest, typical window time frame used by a lot of engineers in the range of 0.2 TN to 1.5 TN. Nabanggit nga yung dun nga sa time history analysis. Yun ay yung ginagamit, karagdagan lang. Ginagamit para malaman ang response ng isang structure depende sa self-weight niya at iba pang loading na i-apply or mai-apply yang by nature man or man-made. For example, yung earthquake nga with or flood. Yung pinakita kanina sa ay yung structural analysis. Tapos may two types para nga pa-solve ang time history ng isang structure. Yun yung true linear or non-linear. Ayun nga, yung consider the acceleration response spectrum nga. Kung mapapansin niyo po, yung red mark, makikita natin na may konting pagbabago sa natural period. Ito ay yung maaaring humantong sa malaking pagkakaiba ng maximum sa acceleration. Since some damage is expected and accepted in the structure sa panahon ng malakas na pagyamig, ang spectrum ng disenyo ay nakadevelop sa overstrength o kalabisan ng ductility sa isang structure po. Next. Inputs and outputs for the time history analysis. Mass and stiffness distribution, the acceleration time period record, the scaling factors, directional factors, analysis time step, and etc. Sa outputs ay displacement, stress, resultants, and stresses are each day step, and envelope values of response. Yung inalam ko yung kung ano talaga ang input definition is a time history can be divided into the three steps. Dito papasok yung modification in the specified model. Ito yung element length na kailangan para sa pinakamababa para sa pagkuha ng mass mode space sa natural na dalas ng system. Yung dun din papasok sa inputs yung mga minimum na sa 10 beses o nominal diameter ng 10D and 6,000 mm. May 5 times of nominal diameter near anchor or land step support and at least one o between two support. Yan yung maaaring isaalang-alang ang mga halaga ng higit pa sa pagsuporta upang makuha ng mas tumpak na resulta sa ng structure. Papasok din yung defining dynamics load for time history. Ito yung input na kinakailangan upang ilagay ang sa spreadsheet for the dynamic time history analysis. Yung slug force ay maaaring calculated by collecting fluid density or velocity. Example yung siko natin, ang tagal ng oras para sa pag-travel sa one elbow ay maaaring kalkulahin by dividing ng haba ng pipe or tubo sa pagitan ng dalawang elbow sa pamamagitan din ng mabilis na daloy. Two-time direction need to be calculated. Iyo ay yung slug duration of slug density, the setting of the dynamic control para sa parameter. May mapapanood naman kayo yung video yan para sa inputs ng ganun. Next po. Time history analysis is advantages. 3 EQ time history retains and second retains natural variance in the EQ time history. 3 allow you to focus response in the periods of interest. 4 relatively easy to do with proper tools. Yeah. Disadvantages, first, usually require lots of time history. Second, greater variance in your computed response. And 3 can take a lot of time to do. Ipapakita naman dun sa video yung mga. Thank you po.
Ito po ay example po ng time history analysis na nakuha ko po sa isang ginamit po na sa isang seminar. Yun po, makikita po natin dito yung mga inputs sa pag-a-analyze po ng structure. Dito po makikita mo natin yung earthquake po mismo. Ito po yung time and yung sa station po. At makikita mo po natin dito kung gaano kalalim. Yung 8.8 kilometers po yung lalim po ng earthquake. And then, ito po yung problem statement. Ito po yung details po ng structure na inanalyze po. Then makikita po natin dito yung frame po ng sa structure. And then, ayun po. May dito po kasi sa time history analysis, meron pong iba't ibang applications na pwedeng gamitin. Ang ginamit po dito ay e-tabs. At gusto po sana naming i-demonstrate kung paano po mag-input po dito. Kaso po, wala po kaming application and naghanap na lang po kami ng videos kung paano po mismo mag-input and paano po yayari yung sa pag-a-analyze po ng ganito sa mismong application po. And po, ito po mga gantong details. Ito po yung mismong lumalabas sa application kapag nakapag-input po tayo ng details about dun sa earthquakes and sa structure po natin. Ayun po. Ayan po, makikita po natin dito yung mga diagrams na sa story drift po, yung sa per story po ng yung kapag move po ng structure, ito po yung by story po. Ayan po. Ayan. Wait lang po. Dito po mapapanood po natin yung example po ng magiging effect po ng earthquake dun sa structure natin. Ito po. Ito po yung pag-analyze sa 1994 North Ridge po na earthquake po sa isang structure. Ito po. Ayan po. Nakikita po natin dito na yung gumagalaw na po yung structure nung after ng ilang seconds po ng earthquake. Dahil po, sabi ko po, dito po sa springs mismo nagsa-start yung earthquake, yung ground motion po, and then pataas po sa structure natin. Ayun po. Tapos ito pong sunod ay makikita po natin yung effect po yung sa details po ng moment diagram po ng building natin per story. Ayan po. Ayan po, makikita po natin na by time, palakas yung nagiging effect po ng earthquake sa moment diagram po ng structure natin. Ayan po. Dito po makikita po natin sa gitna. Dito po yung may pinakamalakas. Ito naman po yung sa shear force. Pero parang dapat nauna pala. Yun po. Ito po. Di ba po nakita po natin dito na dito po yung may malaking moment reaction po dito sa ano. Ito po. Ito naman po yung sa shear. Ayun po. Tapos ito po yung mismong pag-i-input po ng details sa time history analysis. Pero po ito yung medyo mahaba. Ang gagawin ko na lang po ay medyo i-adjust ko po yung play speed po ng video. Kung okay lang po. Kasi super haba po
In this
super haba po. Gawin ko lang po mga 1.25 baka po hindi ninyo maintindihan yung mismong sinasabi po. Thank you po.
lecture, I will discuss how to perform time history analysis in ETAPS. In the last lecture, I have discussed how to download time history records or earthquake ground motions from the peer database. So for performing time history analysis, first run the analysis and then calculate its fundamental time period. Here I am running the model. Okay, now display the form shape. Go to mode 1, fundamental, first mode time period, apply. Okay, here is a fundamental time period of our building. So that is 0.473. Okay, so now I will unlock the model and see the properties which is I have defined earlier. And here is the load patterns. Here is earthquake in positive direction, earthquake in negative direction. Okay, and it is as per UBC 97, seismic zone 3 with soil profile SD have been defined. Okay, similarly here in the negative x direction, all the properties are same. Okay, it is 0.36, 0.54. Okay, now for uploading the time history records before, you have to define the target response spectrum. Target response spectrum is defined as same as I have defined in the previous lecture for the response spectrum analysis. I have shown you three methods 3 response spectrum curves by ASCE 7, by Indian Standard Code, and by UBC 97. In this example of time history analysis, I will define by UBC 97. Here I will put the seismic coefficient, that is 0.36 and 0.54. Okay, here is the default model damping for the structure for this curve, that is 5%. I am naming it target response spectrum. Why I am making the name target response spectrum, I will explain later. Okay, here is target response spectrum. Now I will go in the time history. Here I will go choose function type to add. Here I will select from file, add new function. Here I will browse my file of earthquake record. Here is the earthquake record, which is I have downloaded from the peer ground motion database. Here are basically 9 files, 3 files for the acceleration. Here is A. These are acceleration files, these are displacement files, and these are velocity files. Okay, here is a 180. I will click open. Then I will view the file. Okay, here is the data. Peer NG strong motion database record Imperial Valley, El Centro, earthquake acceleration time series in G units, means gravitation acceleration units. Number of points, that is number of points. That is a deviation interval, that is 0.01. Okay, here I will put 0.01. Second, first 4 line I have to skip because data start after the first 4 lines. And how many points are present on each line? Here 1, 2, 3, 4, 5. 5 points present in each line. Okay, now I have to skip 4 lines, and then a number of points per line are 5. Okay, so here is a time history record. You can view by just making a rectangle. You can see its coordinates. Okay, just by double clicking at any point, you will come back to its original position. And here is I am assigning Imperial 1940 x direction, that is 180-degree angle. Okay, same way I will define the 270-degree file. Here is 180, that is I have previously selected. Here is acceleration 270 file, 270-degree angle file. First line 4 lines have to skip. Then number of points per line are 5. Here is the values at equal interval of 0.01. Okay, so here you can see our, I am naming it Imperial 1940 y direction. Okay, okay, you can see in x and in y direction both earthquake records have been defined. Basically in every earthquake record, basically 3 files we obtain: x direction, y direction, and z direction, means upward. The upward we 99% do not consider because the earthquake when effect to the building or strike to the building, then major part only the horizontal components take. The vertical component do not take much part. So that's why we are considering only x and y. Okay, if you want to consider the z component, then same way you add new function, browse, and here is a up, that is the third function you can use. Okay, but in this example I am using these two. Okay, now why I have defined the target response spectrum. For that, here I will go in the match to response spectrum. I will click here and click add new function. Okay, before explaining, I will go in the ASCE7 file. Okay, first of all, here in this example, I have selected only one earthquake record of Imperial Valley earthquake. So basically the code recommended that up to ASCE 710, that minimum 3 ground motions should be used for the analysis of time history. Here, before the addition of ASCE 7 chapter 16 required a minimum 3 ground motions for non-linear response history analysis. If 3 ground motions were used, okay, then if then highest value of these three, if we analyze, then highest values from these 3 records will be used. And if we are using 7 or more records, then we have to use the mean value. Okay, and the second value, the second thing which is important about the ground motion records, that there is a selection criteria. If we are designing a building at a specific location, then for applying the earthquake records, there is a requirement for the selection of earthquakes. For the selection of earthquakes, these are the parameters that you have to see: the source mechanism, magnitude, soil properties are matching your soil conditions, and the soil conditions of the where the earthquake came is matching, because you have to select the earthquake records depending upon your soil condition, site condition, etc., etc. Okay, and then here is the matching. So there are basically we have to scale up or scale down the earthquake record. Why? Because we are locating our building at maybe some far away distance, or some near to the fault lines. Then we have to match the earthquake record to our target response spectrum. Target response spectrum will be defined as per zone. As I have shown you that how I have defined the target response spectrum, that is zone 3 here. Here I have selected the soil type SD and the zone 3 according to UBC 97. Here I have put the value of CV 0.54 and for the CA 0.36. That is the according to the zone that is given by the earthquake maps. So we have selected the zone 3 where our building will be located. So according to that I have defined the cancel. According to that condition I have defined the response spectrum. Here you can see the target response spectrum. Okay, 0.36 is 0.54. Okay, here is the code saying then you have to whatever the earthquake record, you have to match to your target response spectrum. Okay, here, oh sorry, I will again go in the define functions time history. Okay, here in the choose file, here match to response spectrum, I will click add new function. Here I will click time history, x direction, imperial earthquake time history in x direction. I am scaling first x direction earthquake, then the y direction. There are two types of spectral matching. One is frequency domain and one is the spectral matching in the time domain. I will show you both, then which one is better I will select that. Here I will first of all I will select the function target response spectrum. Okay, here is our target response spectrum, and then which function I want to scale. Here is x direction data. Okay, now here is the set matching pattern that is by default. I will let this program determine automatically. Now I will click match time history. Okay, here you can see here is a blue line that is the actual earthquake, and then software scaled up some value and then make a new earthquake spectral acceleration, and here is was also a new earthquake record with some magnifying factor, the new earthquake. So that is matching, but your matching should be from 0 to t to 2t matlab mean here if I multiply with 0.2t, that is our time period. So that is value another plus, for example, 3 here from 0.094 to 0.946, our earthquake record from this time period 0.2 to 0.9 time period, that our most of the earthquake should match on that side. So how, why I am doing here period range for scaling or matching. Okay, before 2016 it is the value the range is 0.2t to 1.5t, but in the 2016 edition the value is changed 1.5t to 2t. Okay, where t is the fundamental time period of the building. Okay, so in this second, when the matching is happening, but the new earthquake record is not properly managing over the target response spectrum, so that's why I will choose the second, spectral matching in the time domain. Okay, here is again program will automatically determine its parameter. Here I will click match time history. Now you can see again the matching, the second method, spectral matching in the time domain. Software have beautifully matched this. Uh, um, Basically, this is the blue is the actual earthquake record, that is imperial. Then software did the multiplication factor so that it is matching on the target response spectrum very beautifully. Means from 0 to t to 2t value, all the matching have been done beautifully. Okay, so now we will the new earthquake record which is after scaling is the black lines. So now I will click convert to user defined. Okay, here I will click modify. Okay, now it's a simple form of a new earthquake. You can also say that is a synthetic earthquake. Okay, now same way for the imperial valley. I will click add new function, time history in the y imperial. Okay, target response spectrum. Now I will click the y value and select the spectral matching in the time domain. Okay, click match time history. Again, for the y component of earthquake, a good matching have been done. Okay, from 0 to t to 2t. Okay, and now again I will convert this new earthquake record here. The new earthquake record value is, for example, minus 0.15. That is a vertical component. Okay, convert to user define. Okay, I will click modify. Okay, you can again see is it the same value. Okay, so that's how we scale our earthquake record to match the target response spectrum, which will match our requirements of the building where we are going to locate. Okay, so now going to load cases. Here I will define. Here I will delete. Yes, add new load case. Okay, time history x direction load case. Okay, here I will select time history. Again, in the time history, there are four: linear model, non-linear model, linear direct integration, non-linear direct integration. First of all, what is the difference between model and direct integration? Model is the approximate method for the analyzing the earthquake records, and direct integration have a exact values. Means it is a closed boundary solution. Means it take the input value of the earthquake record and analyze it. Direct integration use the full method. So for the analysis of by using direct integration, it takes much time, but it gives the accurate results. Means to the point. And model analysis is approximate, and it will give the results approximate, but in a very less time. You can say within a 10 second or within 15 second. Okay, so for this example, I will use the linear model analysis. Okay, here I will add load pattern acceleration u1 in the x direction. Here I will select the scaled imperial in x direction. Here I will use the multiplication factor. First of all, I will see what is the units of g. Here acceleration units are millimeter per second square, means the g value will be 9810. Here is the multiplication factor, I g divided by r. I is the importance factor, g is the gravitational acceleration coefficient, that is a 9.81, r is the response modification factor. Okay, so here I will put 9810 multiplied by 1 divided by 5.5, means that is a IG, my GI over R. Okay, and press enter. Here is a multiplication factor. Okay, and here is a model load case. Definitely one model we have defined, time history motion type, that will be transient, and how many number of steps will be required in the output. Okay, our total time history record time length is 30 seconds. So if sorry 30 seconds, if I use 0.1 divided by 0.1, then I have to use 300 steps to cover the whole time history record. So I will use 300 with the output time step 0.1. Model damping will be 0.05, mean 5% for this model. Okay, now similarly I will again add copy of this but now time history in y direction. Here I will select time history in the y direction. The same multiplication factor will be there, 300 and 0.1, and hit OK. Here is an advanced option. If and your earthquake do not exactly apply in the x or y, means it is the earthquake is at an angle, then you can use here the advanced option. You can set the angle at where your model earthquake need to be strike to the building, so you can use that option. But here I am using the simple option. Okay, so I have defined the earthquake record in the x and in the y direction as a load case. Okay, so now I will run the analysis. Now I will go in the define load combinations. Here is a predefined load combination. I will select all and delete. Okay, here in the defined load pattern, I do not need the earthquake in y and x. I will also delete. Okay, so these two are needed for the calculation of multiplication factor, means adjustment factor. Okay, I will again go in the load combinations and click add default design combination, concrete frame design, convert to user agreeable combination. Okay, so here are the all combinations. Modify, you can see all the combinations. Okay, here in the earthquake x, you will select instead of earthquake x your time history x reduction load case. Okay, here again, here now the y direction, y direction.
May kasunod pa po 'to,
Okay, now all the
paano din
time
po
history
natin
load
yung
cases are
part
in the
2.
combinations. Okay, okay, now all the time history load cases are in the combinations. Okay, so now I will run analysis.
Wait lang po.
Okay, now all the time history load cases are in the combinations. Okay, so now I will run analysis. Now analysis is complete. Now I will go tables, analysis, results, reactions, base reaction. Okay, here I will select the load combination and the load pattern earthquake x at y. Similarly, earthquake time history load case in x, time history node minimum. Okay, and the y. Okay, so now you can also take the minimum value, it will not affect much. Sorry, earthquake x, earthquake y. Okay, so now you can see the due to equivalent static load method, the values are 5141.9, and due to time history analysis, the base shear base reactions are 2996, means 3000. Similarly, in the y, the value is 5141, but due to time history, the values in the y directions are 1989, or you can say 2135. We have to take the average and calculate the multiplication factor. Here I will show you how. Here is 5141 divided by, here is the average value will be around about 3000, so I will click 3100. Okay, here is the multiplication factor 1.68. So code says that your value, the difference between the values between this reaction and due to time history do not more than 15%. So that's why we have to multiply this lower value to adjust to the to become so much large so that it comes near to this value. So for that I have calculated the multiplication factor 1.65. Similarly for the downward, Here I'm just writing 1.65 for x direction. Let's see what's the value are in the y direction. That will be 21 or yeah. So here I'm putting 205. Okay, 2050, enter. So 2.5 factor in the y direction. I will unlock model and again go to define load case. Here in the x direction we did multiplication factor 1.65. Okay, and for the y direction the value is 2.5. 2.507, so you can ignore. Okay, okay. Now again run analysis and we will see again the reaction values. Now the analysis is complete. I will again go in the analysis, results, reactions, base reaction. So here software updated the base reactions. So now you can see here is a 5000, here is a 4944 and the 536 is now the values are near. But in the y direction again the values are coming in the nearable range. So let's see what's the difference. 4251 divided by 5141. Okay, multiply by 100. The value is 1882. So basically we have to take the average. So 100 minus 82, still the difference is 18%. So, or you can say 17%. You have to again multiply the factor by by calculating the factor. Here you will again calculate the factor. Here is the factor 1.2. So now I will apply in the both 1.2 more factor. Define load cases. Again run analysis and check the reactions. Analysis is complete. Now I will gain in the analysis, results, reactions, base reaction. Here I will again select. Okay, so let's see. Here is the 5141. So here now values are more, but in the y direction now the values are nearable. So in the x direction we have to decrease up to some extent. So let's see, is it within the 15%? 5141 divided by its average will be 62 roughly. So again the 18%. Now we have to decrease in the x direction by applying the factor. Now due to the time history the values are higher, so and it is nearly 15%, approximately 15% the difference, so that's okay. So now I will the analysis is complete, load combination have been defined. Now I will go into design, concrete frame design. Okay, here start design / check. And now the design is complete. Okay, check design, concrete frame design, and verify. 86 concrete members failed in the design check. Do you want to select them? No. So for example, if we want to see the forces, now I want to see the reinforcement in the column. I will right click. Okay, so here is a reinforcement requirement. Similarly, here in the beam, is failing in the shear, so we have to select all the failed beam and increase the size of these beams, and then again analyze and design. This process we will repeat until all the members pass this check. So that's all for time history analysis. Have a nice day. So you can also see the deform shape due to time history analysis display. Show deform shape, for example, due to time history. In the x direction here, apply, that is a 0 second. Okay, so we have 300 steps, so now I am putting the time step, for example 33, apply. Okay, now the beam is deforming. So we can also select the absolute maximum or absolute minimum. For example, here is maximum, apply. So that's the maximum deformation. Similarly, minimum. Okay, so that's coming towards the my side. So here absolute maximum. So you can see the what the deform behavior at any time step. Okay, so you can also see display plot functions. Okay, or response plots, for example plot functions. Okay, here right now the software is showing what time and base shear in the x direction. So here is the maximum and minimum values. Okay, so at 2.4 second, around about here, the maximum base shear is 5933 kilonewton. Okay, similarly you can also see in the y direction. If this is not available in the y direction, then you can from here add new function, and that will be base force. Okay, and base shear will be in the y direction. I am changing the name, its name, that is base fy. Okay, then I will move towards here, and fx is, now I want to see in the y direction. Right now it is in the x direction. Okay, okay, now you can see in the y direction. Similarly, you can see many more functions as you have seen. Okay, for example here you can define new functions, story forces, spear forces, joint velocity, joint displacements, any. Okay, so all these forces you can see in the time history analysis. So that's all for the time history analysis. Have a nice day.
Ayun po, kita po naman natin yung, ah, ah, advancement po nung paggamit ng applications. Dahil nag-i-insert po tayo ng mga details, and nakita po natin yung naging epekto nung earthquake sa ating structure. Kitang-kita po natin yung pagiging deform po ng vertical and horizontal members po ng ating structure. And ang interesting lang pong matutunan ng ganito, lalo na po kung magagamit natin sa field. Ayun po. Then next po.
There are other methods to match the design spectrum. And let's talk about the second method, the spectral matching. Involves a time domain engineering para ang response ng spectrum ay dapat compatible sa smooth target spectrum. Pwedeng polyline design spectrum or a hazard spectrum. Pag sinabing spectrum, ito yung curve na nagpapakita ng amplitude and phase as a function of frequency or period, or how much of each type of shaking there is from earthquake. Makikita natin ang sample ng spectrum sa next slide. Based on the original method proposed by Kiad Linhanat and Wen S. Cheng in 1987 to 1988, the summary of this method describes the development and application of a new method for generation of realistic synthetic earthquake time histories compatible with the multiple damping minimizing perturbation on the characters. It also demonstrates that seismic responses of structures based on those obtained from analysis using an ensemble of time in 1993. He is engineer in seismology who wrote the first it means response spectrum just ang earthquake accelerograms. Para mag-match ang specific target response spectrum gamit ang wavelength algorithm proposed by Abrahamson. And it was subsequently updated by Hancock in 2006, a little more stable and faster. Spectral matching has the advantage of significantly reducing variability in the computed response because the time history of spectral matching. First, next slide po. Next, the response spectrum based on spectral matching. So usually requires fewer ground motion. Sometimes easier to spot design flaws from the system response. And the disadvantages of spectral matching can result in unrealistic earthquake ground motion. Two certain valuable aspects of earthquake time history can be lost. Can take a lot of time to do correctly. Easier to grow up if you don't know what you're doing. And the next slide,
Medyo may kahabaan lang din po ito.
So, okay, this is the interface of Seismomesh, and it's very simple, just one-step process. In the two-step process, first you define the target spectrum, you actually import a ground motion, and then just click on do matching. So let's open a particular ground motion file. So I click on open single. I can also go for open multiple, but let's first go to open single, one file. So here